All right, so we just heard about Laplace and Fourier transforms. Again, I think I told you these are fascinating subjects. I just want to sort of build a little bit on Laplace transform because we'll be using this quite often. And if we are looking at positive valued functions, and let's say they are well-behaved positive valued functions, and positive valued means to go from 0 to infinity. So the Laplace transform of a function, let's say I denote that as f hat, 0 to infinity, e to the power minus f of t dt. So just like in the Fourier transform, what we found was the Fourier transform is like a moment generating function, because I can expand the exponential function and basically do term by term integration. And if f of t is like a probability density, positive value, because it goes only from 0 to infinity, I can essentially do the same thing. Yes? You are not able to hear me? Yeah. Alright, I'll try and speak louder. This should catch. So if f of t, if you think of that as a probability distribution function in time, as an estimate, what I was saying was the Laplace transform is also a moment generating function then. And therefore, if I were to define, let's say well, I'm not sure I'll be consistent, but let's say nth moment of f of t, if that is defined like this, then basically following the exact same arguments, you're going to expand, take derivatives with respect to s, you will essentially have that the nth moment minus 1 to the power of n evaluated at s equals 0. Same argument, nothing is changing. We don't have the complex number, we have minus sign, and therefore we have this minus 1 to the power of n. All you are doing is expanding this in an infinite series, doing term by term expectation, and you will get this. So Laplace transform also gives rise to moments. It's a moment generating function. And as Dr. Gula was pointing out, we have Fourier transforms, we have Laplace transforms. What we hope never to have to do is to take an inverse transform, either a Fourier or a Laplace, because neither of those are intuitive or easy operations. What we are hoping to do in this course is when we do Laplace transforms, we'll simply find the Laplace transform and then use this operation to find the moment. And if you are interested in moments, that is where we stop. We do not need to be taking inverse transforms. The other fact that we will use quite often is if you think of the advection dispersion equation, it has derivatives for concentration with respect to space or concentrations with respect to time. Okay, so f of t, in this case we are doing operations in time. I could have replaced with c of x of t. Then this would have become the transform would be a function of c of x for a given x. The transform variable is still s, so that would be fine. If I have to take the transform of a derivative, so let's say I'm going to take the transform of df dt. Okay, so that will by definition be 0 to infinity e to the power of minus s of t df dt dt, and then we will essentially do integration by parts to get, and then I will have a minus and a minus s So this is simply integrating this by parts. So whenever I have expressions which have concentration of something with respect to time first, if I take the Laplace transform, this is what I'm going to get. This I have to evaluate at the two limits, 0 and infinity, I'm sorry. So at infinity, e to the power of minus st is going to 0. S, excuse me, the transform variable, we will assume it's always positive. And our functions f of t will essentially be concentration profiles, which will be very well behaved, so we don't have to worry about the similar problems that could arise during inverse Laplaces. And we will, like I said, we will not be taking inverse Laplace transforms. So at t equals infinity, it's 0. At t equals 0, this is 1. So basically, minus s and minus of minus becomes plus. This simply becomes, so notice that this is the definition of the Laplace transform minus the value at f equals 0. So these are results that we will be using for Laplace transforms. So I thought I would essentially, start with that, and then we will continue with again coming back to the idea of solute transport equations, and where we talked about transforms. How do we try and relate those two? So in this lecture, my goal is to visit various transport models. And thank you. We will also try and answer some of the questions that had been raised earlier regarding what happens with absorption, where is that, and how do we manage, or how do we work with some of those. Excuse me. This was a problem that you sort of saw yesterday, and I basically presented only for completeness. So if I have pure diffusion in porous media, so this is the simplest case, then the diffusive flux is given by this expression. Notice that C sub r is a resident concentration, as we talked about. The governing differential equation looks like this. Eta is the porosity in this case. So this is how the total mass in the control volume changes. This is how the flux coming in and out of the control volume. We combine these two equations to get what is called the diffusion equation. And we talked about this. We can have different boundary conditions. So just as we talked about, in this case, for the resident concentration, which is a function of S and T, I can define a Laplace transform. I don't have to call it a Laplace transform. Let's say I define a transform like this. Okay. And if I then do the Laplace transform, notice that because this has a C sub r del C L sub r dt, I'll have this term. Initially, the concentration is 0, so this part is going to be 0. And you'll get an equation which looks like this, where lambda square is defined by this expression. The boundary conditions which we had in the resident concentration in the transform domain will look like this. And then for this is a fairly simple solution to this equation. And you get the Laplace transform x and s. In this case, this expression is simple enough that you can actually invert it and get the resident concentration as a function of space and time. And it is in terms of complementary error functions. So I just present this for completeness. This is not what we'll be doing in the rest of the class. We do not ever, or we do not really envisage having to take the inverse and get back the function. Okay. We would essentially want to work with this transform and hope that we can directly get to moments from there. So if you're interested in moments, we just want to do that. And this realization that I can have differential equations, simply get the transform, not worry about the inverse, and use the transform to directly calculate moments is what all moment analysis sort of revolves around. Okay. So this sort of realization, if you will, or this idea was essentially first discovered by Aris. So it's sometimes called as Aris's method. It is very nice for many, many reasons. First is, as was pointed out, when you do a transform, there are various reasons why one might want to do a transform. So this is a partial differential equation. When you do a transform, it becomes an ordinary differential equation because we integrate out one dimension. So we have made it a much simpler equation. Solving that much simpler equation is fairly straightforward. Okay. And you get essentially an expression for the transform. If I can simply take derivatives of this, using this idea and get moments, I made my problem much simpler. Otherwise, notice that what I would have to try and do. So if I was going to use a transform method, let's say I'm looking at a flux concentration, I would have C of f of x of t. I would take the differential equation let's say I apply the transform, I'll get C of f hat. I'll get an expression for that. Sorry. If I take the transform, I'll get C of f hat, which is a function of x and s. I will take the inverse transform to find out what C of f of x of t. I don't initially know this. I have a differential equation for this. Do the transform, get it, take the inverse transform, get this, and then to calculate the moment, well, if I want to calculate the moment, then I have to do this operation, 0 to t, t to the power of n, C of f of x of t dt. So assuming I could do all this and find an expression for f, then to do this integration would be extremely difficult, very difficult. Okay. So all that is, we hope to bypass all that. And that is going to be our strategy going forward. So let us start with the advection dispersion model. We have seen this yesterday. So our basic equation is this equation. Remember, C sub B is the bulk concentration. So if I have, let's say, water moving in a soil column, I take a unit volume. The bulk concentration is the total solute that exists within that bulk, in that volume, C sub B. Q sub S was a solute flux. So in this case, we would be measuring how much solute flux is entering from the top, leaving from the bottom, take its difference. That is this term. So if I have no sources and sinks for solute, this is essentially my conservation equation in most general form. It's always going to be true. Whether we have retardation, whether we have not, how is solute moving, all of those will have to be buried in either C sub B or my expression for Q sub S. Okay. What we also said is we defined C sub F. Remember, the C sub F, the flux concentration, was going to be the solute flux divided by the Darcian flux. So I would get this expression. Or if you recall our expression for C sub F, we can write it in terms of resident concentration, and you would get an equation of this nature. Q sub S is given by this quantity, the solute flux. C sub B, the bulk concentration, assuming in the advection dispersion equation, in this form we'll assume that solute only resides with the liquid phase. There's nothing in the solid phase, nothing in the air phase. So the bulk concentration is simply porosity times the resident concentration. The Darcian flux is the porosity times what we call as the seepage velocity. And this is our definition for C sub F, the flux concentration. Okay. Initial conditions, in the soil, whatever the concentration is, let's say we define it in terms of bulk concentration, C sub B. At the inlet, what is happening at x equals 0, the flux concentration as a function of time is some function. And we had this discussion also when Professor Srivastava was talking about it, about the various kinds of boundary conditions. And assuming we all remember this, or we will basically, let's say I have again a soil column. Okay. So this is all soil now, and I have water flowing in this direction. Let's say it's all steady state. This is my inlet end. So at the inlet end, essentially I am adding water continuously to it, and it may have some solute mixed in it. So he basically was talking about a boundary condition which essentially said V times C0 was going to be equal to V times C minus B del C. Well, let's call this as a x direction. So del C del x. And so this boundary condition actually has a lot of history. Notice that if I were to multiply throughout by eta, or the porosity, I will have eta here, and eta here. You will recognize that this quantity over here is the total solute flux. Okay. This quantity over here is also solute flux, but now this part is not in the porous medium. So what we are saying is at the boundary, whatever flux is coming in from here is the flux going into the soil. So we are equating those two fluxes at the boundary. And that is what that boundary condition is. So what happens is, so in this construct, notice that this C0 is the concentration of the inlet fluid. Okay. If this is supposed to be flux, by our definition, this would be the resident concentration. That would be Q sub S. Okay. If I divide throughout by eta, or if I divide throughout by V, I'm going to get C0 equals C sub R minus D over V del CR del X, which you will notice this part is at, wow, is what we define as a flux concentration. So this mixed boundary condition, or sometimes called as Danforth's condition, where if we are using a Dirichlet kind of condition over here, we are saying concentration at the inlet is the concentration at the boundary, we are actually imposing that condition on the flux concentration. If we are essentially imposing a condition like this, we are saying V times C0 is V times CR minus D del CR del X. The concentrations, then we are talking about a resident concentration. But otherwise, physically, they should be doing the same system. Which equation you use or what you are using depends on what it is you are trying to solve. It just so happens, and again, Professor Srivastava pointed this out to you, the resident concentration and the flux concentration, they obey the same equation. Advection dispersion equation, the governing differential equation is the same. The only thing different is if we are dealing with resident concentrations, this becomes your boundary condition. If it's flux concentration, this is your boundary condition. The flux concentration boundary condition is much simpler to implement. Otherwise, they should give you consistent results. So what boundary condition we use is matter of also, what concentration it is that we are looking for. So back to the advection dispersion equation. So that's why at the inlet end, if I impose my end condition in terms of flux concentration, I can have a very simple Dirichlet condition. Now, let's go back to this equation. So this equation, like I said, this is a basic continuity equation. Del Cv del T plus del Qx del X. And notice that this is now in terms of C sub F. So this equation allows us to relate bulk concentration to flux concentrations. And if I integrate the two, this gives me this particular expression. Okay. So all I've done is integrate throughout with respect to time. So that's the same equation. And if I will take Laplace transforms of this equation, which means I'm multiplying throughout by e to the power of minus st, all the terms, doing integration, Cb0 of x, it has no term in t, so integral Laplace transform of a constant is simply 1 over s. So you get that term. This is Cb of x of t, its Laplace transform will denote as Cb of hat. This term over here, with e to the power of minus st in front and the integration from 0 to infinity, again, if you use integration by parts, you'll get this expression. And then what this expression allows you to do is, if you have solved, let's say you go through the process and solve for the flux concentration, this expression tells you what the bulk concentration Laplace transform will be. Okay. And this will be very useful later on. Okay. I can do the same thing. Instead of integrating with respect to t, the previous continuity equation, which I call our basic equation over here, if I integrate with respect to x, I'll get an equation like this. I can take Laplace transforms of that as well. And if I go through some of the algebra, I'll get this expression, which now says if I had the bulk concentration Laplace transform, I could actually calculate the flux concentration Laplace transform. Very, very useful results, as we will see. One of the things I will also point out before we proceed further is notice that this continuity equation C sub B is bulk concentration, Q sub S is the flux. And we talked about random variables and taking expectations and so on. Later on, we will see how we use this continuity equation to relate two different probability distributions. And that is where it will all start to tie together. Okay. So if I have the flux concentration, my equation for the flux concentration, assuming D and V are constant, has the same form, exact same form as the resident concentration equation. The governing equation doesn't change. The only thing is the boundary conditions in flux concentration are much simpler. And what we will start by doing is having a condition where we say that we are going to add a certain solute mass at time t equals 0 at the inlet n. Okay? And that will be our condition, which we will replace, which will indicate by a delta function. Delta of t essentially means this has a value of 1 when delta t equals 0, otherwise it's 0 everywhere else in time. So if I'm adding a mass of solute m, okay, I have to divide by q times a. Remember, q is the Darcian flux, a is the area of the cross section. So this is actually capital Q, the total flow rate that is going through the column. So if I do this, and for convenience, I don't have to. For convenience, I'll essentially call that value of 1. So what that will essentially do is, eventually my flux concentration will effectively have a total mass of 1, which will also allow us to relate it to probability distributions. So we will do all of that. All the other boundary conditions simply say that initially the soil is solute free, the outlet other end is at infinity. So we assume that the soil column is infinitely long, as Professor Srivastava was saying, and any place that we want the solution, we essentially find the solution at that x. So at infinity, it's far enough that whatever we have done at the inlet end, the solute plume does not move that far in the duration of time that we are interested in, so that boundary doesn't have to play a role in our solution. But having this set to 0, therefore also simplifies our transforms. Okay, so this is what we are going to be working with. So the two important relations are this one, because this relates CB hat, which is the Laplace transform for the bulk concentration, to the Laplace transform for the flux concentration. So if I take the advection dispersion equation, this one, notice that del CF, del T, this essentially will become S times the transform. These are derivatives in space, so basically the transform simply moves through, and we will have del square CF hat, del CF hat, and so on. So a transformed equation looks like this. The transformed equation looks like this. This is a second order differential equation, okay, with constant coefficients, and we can solve for it. Are all of you familiar with how to solve for this? Remember, if you have a second order differential equation, you essentially find the characteristic roots, find the solution, which is sum of exponentials. One of the exponential will disappear because we will have 1 minus c of 1 plus c, let's say. 1 plus c, c is always positive. S is a positive number. So exponential of that positive quantity will become, it will go on increasing unless we make that coefficient equal to 0. So we'll only be left with one term. Since we chose our normalizing constant to be 1, we will essentially get this expression. So this you either have seen before, or you'll have to talk to me and I'll derive it for you. But it's a fairly straightforward thing to do. What that does give us? That gives us C of x comma t. Sorry, C of f hat of x comma s looks like this. C looks like this. Okay. So this is S, the transform variable, D is dispersion, V is velocity. In this case, this CF hat is simple enough that I can look up the inverse transform using Laplace transform tables. So this is the solution to the advection dispersion equation, assuming a Dirac input, assuming all the probability mass is applied instantaneously and it moves through the column then. And at some certain distance x, you will have this solution. It is not the normal distribution. Okay, the normal distribution actually comes in later. And as we was also saying how we relate the variance to the dispersion and so on, we will see where that comes in and what the ramifications are for doing that, perhaps in some of our other lectures. What I have not given you, now that I realize, is if I have Cf hat, which is this expression over here, I can actually calculate Cb hat from this. This part is 0 because initially this is solute free. I have Cf hat, which I just calculated. I can substitute this, and after a little bit of simplification, I'll have an expression for Cb hat, and even that can be inverted in the simple case, and you'll get a long expression. But I wish I had kept the expression for Cb hat. So what we would therefore, basically the model over here is, therefore we get this, essentially the Laplace transform of C of f hat in terms of x and s. If I wanted to calculate moments, by our definition for moments, I would take the derivative of this with respect to s. Whatever derivative I take set equal to 0, that will start giving me moments of C of f, of the flux concentration. Okay. So at any, if I have a column of any length x, I'm observing the breakthrough curve or the amount of solute that's coming out as a function of time. I'm calculating the moments of that function directly by using this expression. I'm not ever having to use this whole solution, but we'll keep it in mind for various reasons. This is our solution, what we'll call as the advection dispersion equation model. So what it says is, if we believe, this is, you have to believe this to some degree, that the advection dispersion equation is the right model to use, and you observe concentration as a function of time, flux concentrations, you can fit this quantity. And you would get expressions for D and perhaps V. And we talked about, and then Professor Srivastava talked about how to get D and V using some idea like this, but of course he was talking about a different boundary condition. He had the concentration be kept at C0 all the time. It is a step function, not a delta input. Nevertheless, I do want to point out that we expect V to be known to us, because I'm doing a column experiment. If I'm measuring how much flow rate is going through the column, and if I know the porosity, I should have an independent estimate of V without having to use this to find out what V is. If I basically do my experiment and the first moment of my breakthrough curve, which tells me sort of the average time, and use that to calculate V, and it's very different from this V, then let's say that velocity that I'm getting over here is much smaller than what I would expect, then I would suspect there is retardation. Otherwise, beforehand, I would not know if there is retardation occurring in the soil or not. So V actually should be given to us simply by the flow experiment. I don't have to do anything with concentration to know what V is. Right? D, I pretty much have to do some kind of an experiment to know what a dispersion is. Everybody with me so far? So this is the basic idea. Now what we would like to do, so the advection dispersion equation is one model. We will see what happens when we have other models, what kind of parallels we will draw, and later on we'll talk about a different class of models too. For this, so the advection dispersion equation is not given to us by God. We basically derived it. We said, I'll assume this is what is happening. This is my definition for flux. Okay. There are other models also, and there are perhaps very good reasons for looking at these models. Is this in focus, or am I standing too close? So the advection dispersion equation essentially, if you think what it's doing, it's obeying Fick's law. It basically says this is how we will govern concentration movement. There's going to be advection, and the dispersion will model as Fick's law. A mobile-immobile model formulation is different. It allows for different things, more things to happen. What it says is, I'll conceptualize the soil as if the soil, has small soil particles, but also has aggregates. And these aggregates are like larger soil particles which have openings within them too. And if it's completely saturated, water will fill the smaller openings, but the main bulk of the water, this water is essentially locked up, and it's very difficult to access this water. There's dead-end pores and so on. So they do not contribute to active water movement. So what we try to conceptualize, therefore, it's a conceptualization. We say that the total pore space that we have the normal pores, but then we have water trapped in what we'll call as immobile regions. But so that will not contribute actively to advection anymore. However, when we have solute mixed in it, the solute will slowly diffuse into these aggregates through the water, and then it can slowly diffuse out, but the water itself cannot move. Okay. So that means we have added an extra bit of complexity in our model. We think some other things are happening. You would have a reason to say, why would that happen? Very likely what would happen is you would observe our concentration, flux concentration behavior as a function of time and say this doesn't look anything like what this should be looking like. Okay. It has perhaps a very long tail, something else is happening, and then you say, well, my simplistic advection dispersion equation model is not enough. There are other phenomena that are occurring that I should be looking at. So one of them, the next level of complication, would be essentially this mobile-immobile model, where we will assume that the soil is divided into the actual solid pores, but the pore space has two compartments. One is theta. Theta m is the mobile water content fraction. Theta im is going to be the immobile water content fraction. So total theta, if it is saturated, theta m plus theta im, which is the total water content, that will be equal to the porosity. Right. What we then say is that the resident concentration that is associated with the mobile water is C sub m r now. Okay. The m now stands for the mobile part. R is of course resident. Similarly, for the immobile region, we will conceptualize that the concentration of solute that is associated with the immobile region is CIM, also resident concentration. And we will keep it simple, and that is what is happening. So what changes now? If this is our definition, again, there is nothing happening in the solid phase, there is nothing happening in the air phase, so my definition for what is bulk concentration has changed. It's going to be theta m CMR plus theta im CIMR. What is happening to my expression for flux? The soil particles are still not moving. The only way water will move is if it's part of the mobile water, and that's where the solute will also move. Whatever dispersion is going to be occurring will have to be occurring with this mobile water part. So my definition for flux is essentially the same, except that instead of simply being C resident, it is C mobile resident. Okay. The dispersion that occurs in the longitudinal direction is going to be based on the derivative or the gradient in the mobile concentration, resident concentration. So this becomes my definition for total flux. My definition for the flux concentration in the mobile region is simply Q sub S over Q, same definition. Okay. But now I add this M to indicate that this is flux concentration but associated only with the mobile region. So now what happens to my differential equation? Notice our differential equation is still this one. It's always this. Del CB del T plus del QS del X equals 0. Our definition for C sub B has changed. Our definition for Q sub S has changed in the sense that we now only associate C mobile resident concentrations. Otherwise, it's the same. So if I now basically go back and substitute that, this should be the derivative of the bulk concentration with respect to time. So I have theta m del CMR del T, theta im del C IMR del T. So this is the change in bulk concentration with time. This is the flux definition which we had over here. Remains the same. But now we have added another unknown variable. We have a CIM of R in our equation over here, which is mostly in terms of Cm of R, right? So one more equation is needed. What we assume is that from the mobile region to the immobile region, solute can mix. It will slowly diffuse through. And this diffusion will occur in proportion to the difference in the concentration of the mobile and immobile regions. So that means the rate at which this immobile concentration is changing times theta im, we will assume is proportional to this difference times some rate parameter, we'll call that as alpha. If alpha is infinity, that means if I divide throughout by infinity, I'll have CMR equals CIM of R, which means the mobile and immobile concentration are the same, they have equilibrated. If they are different, then there will be some gradient or some solute moving either from the mobile region to the immobile region or the other way, and that will simply depend on this sign. If CMR is greater than this, water is moving is greater than CIM, that means the solute is moving from the mobile to the immobile region, otherwise vice versa, and that's how this is changing. So that gives us how this term will change. So another equation. So this is something we assume. Okay. We say we think the soil is more complex than just what we had initially. So still within the construct of what we would call an advection dispersion equation. You would then again have boundary conditions. On the mobile region, concentration will say it's initially free of solute for both mobile and immobile regions. The mobile flux concentration to infinity will keep it as 0. The mobile flux concentration at the inlet n, again we will assume it to be a delta function. That means all solute is added instantaneously, and then we essentially have it move through the column. Any questions on the mobile immobile model? So now what do we do? So we will again take Laplace transforms. So when I take Laplace transforms, notice that each of these will have a s term times CMR hat, s times CIM hat, and then this will simply be CMR hat because these are derivatives of space. What this will do is essentially allow us to relate CIMR hat to CMR hat, and therefore wherever I have CIMR hat, I can use this expression to replace it over there, and therefore get one equation only in terms of the Laplace transform for the mobile resonant concentration, or conversely for the mobile flux concentration. So that's going to be our strategy. So we define the Laplace transform for the mobile resonant concentration in this form. Similarly, transform for the immobile resonant concentration in this form. We go ahead and do all that substitution. We'll get an equation which looks like this. We will have this is the dispersion term, this is the advection term. Now we have this term, everything in terms of CMR hat, and G sub S is a function of S. The flux concentration and the resonant concentration, we essentially have the same equation. And you can show that. We don't do that, but you can show that they will always obey the same equation. Okay. Now what has happened? The only change is in this G sub S. Let's go back to the advection dispersion equation. We had this form. Here, G sub S was simply equal to S itself. Okay. When I come over here, I have essentially the same equation, but now G sub S is a slightly more complicated equation. It's S plus all of this. If theta immobile, that fraction was 0, that means there's no immobile water, all the water is mobile, then G sub S is simply equal to S, and we are back to the advection dispersion equation. Okay. And I can essentially go ahead and find the Laplace transform of this quantity. That means I'm going to be solving this differential equation. It has the same form, but the only thing that has changed is G sub S. So I get a similar expression. So now I have a G sub S over here in the terms C. If I go back to the advection dispersion equation, notice that this was simply S. Okay. Now I have a G sub S. So if my strategy is to find moments, I'm going to be taking derivatives of this, whatever order derivative I want, set S equals 0, and that will give me moments. So the expressions for the moments also are going to be the same, except that when I try to take derivatives, my G sub S term is going to be a little different. So if I take derivative with respect to S, I can take derivative of all this with respect to G, and then del G del S, product rule. Only the dG ds part will keep changing. Otherwise, it's the same as the ADU. Okay. So for moments, this construct remains the same, and that is going to be one of our advantages. Okay. Once I have CMF hat, the bulk concentration transform is going to be given by this. Again, takes a little bit of algebra, but the same idea, because the relationship between bulk concentration and flux concentration was simply based on the continuity equation, and that hasn't changed. So that also remains constant. Any questions? Okay. Let's see physical non-equilibrium model. Okay, so these are all different models where we conceptualize the different things that are happening in the porous media, because we try to account for different effects. The physical non-equilibrium model essentially has, it has got more going in. It has mobile regions, immobile regions, but now we say the solid phase, there is going to be some concentration attached to it. Okay. And so we have to essentially now talk about how we try to incorporate that effect. So our soil We will again define it to mobile and immobile regions. Theta sub m, same definition. It's the water content with mobile water, and the associated resident concentration is C sub mr. Immobile region, theta sub im is the water content, CIMR is the resident concentration associated with it. Then what we also assume is that along with the mobile region, okay, I have soil particles where some of the concentration some of the solute can stick to the soil particles, and therefore S sub m is the solid phase concentration associated with a dynamic soil region. This dynamic soil region is in direct contact with the mobile water. Then I have some stagnant soil region, that means soil which is in direct contact with the immobile region. I'll say that the solid phase concentration is S sub im. And on the total solid phase, I assume that the fraction of soil that is attached, let's say, to the dynamic soil region is F. 1 minus F is then attached to the immobile region. Again, this is how we conceptualize it. So physical non-equilibrium essentially says, we have these soil regions. What we will also assume, is at equilibrium, and in fact this is a little more complicated. S sub m is a solid phase concentration. It is related to the liquid phase concentration by this expression. So it's simply a constant times CMR. So a lot is happening over here. We are assuming that the solid phase and liquid phase concentrations are always at equilibrium, and they are related through this simple linear expression. Doesn't always have to be like that. Similarly, at equilibrium, the solid phase concentration that is associated with the immobile water and the concentration in the resident water, these two are given by this expression, what we would call as linear adsorption at equilibrium. Our definition for flux is still the same. Advective flux has to happen in the mobile region. Dispersive flux has to happen also in the mobile resident concentration. My flux concentration definition also is always going to be Q sub S over Q. I come over here, the total theta, the total water content is the sum of these two, but my C sub B, the bulk concentration definition, has changed, because in a unit volume, now I have mobile region, and the water content is theta sub m. Cm sub r is the concentration in the mobile region. So this is the mass of solute with mobile water. This is the mass of solute with immobile water. This is the mass of solute that is existing with the dynamic soil region. This is with the stagnant soil region. So whatever is happening with the soil is still then part of C sub B. Our definition of flux hasn't changed, because solute is going to be only moving through the mobile resident water. Nothing changes then. Our definition of C sub B has become a little more complicated. We also now need some other, apart from these two equations, okay, we also have to have another equation which essentially connects. So from the mobile concentration to the solid phase concentration, we have these relationships, and we're assuming that those happen instantaneously. The exchange between mobile water and immobile water, these concentrations, we will essentially have an expression like this, similar to what we had for the mobile immobile water. This is the total solid phase concentration. How that will change is going to be proportional to the difference in the concentrations in the mobile water, the solid phase, with the mobile and immobile regions. Proportionality constant alpha. This is called physical non-equilibrium. So we have made, I guess, what we think is happening within the porous media, we have added lots of other things to it. So we come back to the equations, and now we have a lot more equations. This is our basic equation, that our convection dispersion equation. Now we have mobile region concentration in the immobile region, solid phase concentration for the dynamic region, solid phase concentration for the stagnant region, and then one that relates how fast water moves from the mobile to the immobile regions. Now, in general, the mobile water concentration and the solid phase concentrations, they don't have to be linear. they can be, even at equilibrium, they can have a nonlinear relationship. So sometimes we use a Freundlich isotherm. We will select n equals 1 to keep this linear. And if we do that, these are the two equations that we are going to get. So this is again change in bulk concentration with respect to time. And this is the advection term, this is the dispersion term. And then this equation, which essentially relates the mobile resident concentration to the immobile resident concentration through this rate term. Otherwise, nothing else has changed, but we have added more features to it. Our boundary conditions are going to be initially free of solute. At infinity, nothing is happening. At the inlet end, the flux concentration is all the mass is being added instantaneously. And then we can take Laplace transforms of these two equations, and it will be the same thing. You'll have a S term, this will become Cm hat R, this will become Cim R hat with another S term. Here, both of these will simply become Cm R hats because these are spatial derivatives, and then this equation will relate Cim R hat to Cm R hat, which will then substitute over here to get one equation. So if you do all that algebra, so these are definitions for the Laplace transforms for the mobile and immobile concentrations. We do the algebra, so notice that all we are doing is adding an S terms with the time derivatives, these remain the same. Another equation for the physical non-equilibrium. This allows us to relate Cim R hat to Cm R hat. We go ahead and substitute. We get another equation for the resident concentration. The flux concentration follows the same equation. What has changed? Now our definition of this G sub S is much longer. Now we have a lot more things happening. Otherwise, same model, same framework. So G of S looks like this. It's Laplace, we can essentially go ahead and solve for this equation so that I can get an expression for C flux concentration for the mobile region has the same expression. C is the same. The G sub S definition is the only thing that's going to change. CB hat will also have the same expression. All that changes is what G sub S looks like. So what we were trying to show is as we keep changing the models, our basic structure remains the same. My strategy for taking derivatives of CMF hat with respect to S also remains the same. If I write as a product rule, the only thing that keeps changing is the derivative of G of S with respect to S, because G of S keeps getting more complicated. But that's a simple derivative, far easier to do than trying to do the Laplace transform, take its inverse, multiply with x to the power of n and try to integrate all of that. You will not be able to do that. So this is basically the advantage, I think, of this method. Again, let me briefly stop here to see if you have any questions. Let me introduce another model to you. It's called chemical non-equilibrium. So the previous one was physical non-equilibrium. Chemical non-equilibrium is a slightly different construct. It essentially says that within the soil we have one mobile region, but the solid phase that exists, there are some sites where the exchange with the solid phase and the liquid phase concentration is instantaneous. But there are some other sites in the solid phase which are not that directly accessible to the mobile water. It's a rate limited transfer, it takes time. So instantaneous exchange versus much slower exchange. This is what I call as chemical non-equilibrium model, because those can be chemical reversible reactions in this case. So that is, so we define type 1 solid phase sites and type 2 solid phase sites. Type 1 solid phase sites, we will say the reaction is immediate. So the moment the mobile concentration changes, the solid phase concentration changes immediately along with it. Type 2 sites, it's proportional to the difference between the two, and so there is a rate limited reaction there. So what happens to our conceptual sketch? We have a mobile region, only one mobile region. So theta is the water content, C sub r is the resident concentration. Type 1 adsorption sites, the fraction of the soil that has type 1 adsorption sites is capital F, therefore type 2 adsorption sites are 1 minus F, the total solid phase. The solid phase concentration here in type 1 sites is S1, in type 2 sites is going to be S2. So my definition for the bulk concentration is essentially how much solute mass is there in each of these different compartments. theta times C sub R is going to be the solute mass in the resident phase with the mobile water. Rho times S1 plus rho times S2 is the amount of solute in type 1 sites and type 2 sites. So that is my bulk concentration. My definition for the flux, solute flux, is the same, what we had before. Therefore, definition for flux concentration is also the same. What is happening with type 1 sites? For type 1 sites, S sub 1 is K sub D F times C sub R. Okay? K sub D is the rate exchange coefficient. But this is instantaneous. That means as soon as C sub R changes, S sub 1 changes immediately according to this relationship. For type 2 sites, if equilibrium were to be attained, it means if we waited long enough, we would have a similar relationship. Okay. However, the rate at which therefore S1 changes as a function of time is simply whatever is happening with C sub R. C sub R changes, S1 also changes. For type 2 sites, the rate at which the concentration of the solid phase changes is proportional to alpha 2 times, whatever is there in the liquid phase that is associated with type 2 sites minus the concentration in the type 2 sites. So if this difference is very large, let's say this is very high, C sub R is very high, S sub 2 will increase because a lot of the solute will move from the resident concentration into the type 2 sites. But it will be governed by this factor alpha 2. If alpha 2 were infinity, that means the speed is very, very high, which means this equation would hold, and then we would have essentially no non-equilibrium. They are all at equilibrium. So when we do this, so this is another conceptualization. Our governing equation, if this is C sub B, this part over here is simply del sub B del T. Change in bulk concentration as a function of time. The right hand side is the flux. Same equation again. The second equation that we get is essentially combining this equation is the same as this equation. We have simply taken the terms outside. So everything over here, because S1 and S2, their S1 is related with SR, we get this expression. Rho del S2 del T remains over here, but notice that del S2 del T has another equation over here. So I have this equation, I have to combine with this equation. These are the boundary conditions. Again, everything, soil is initially clean. The only thing, the way solute is entering is at the inlet as a flux concentration. And it has a certain mass, but we have normalized it to 1 for convenience. So if I now take Laplace transforms as defined like this, I'll essentially get these two equations. I'll have S2 hat, CR hat, but S2 hat I'll get another expression from here, substitute back, I'll get another equation like this. This is in terms of CR hat. CF hat has exactly the same equation. So the flux concentration follows the same equation. What has changed? The form is the same. Now G of S has a different expression. So my expression for CF hat is also the same. CB hat, also same expression. The only thing that changed is our definition of G of S. So basically now you begin to see the trend. We start with a simple advection dispersion equation. Whatever bells and whistles and complications we add, in this construct, it actually still remains the same. Our bulk concentration definition changes. Our definition for solute flux does not, because in none of these examples we have any part of the solid phase moving. The only way solute is moving is through the mobile liquid concentrations, either as advection or as dispersion. And therefore, this equation always keeps the same form. So does this. The only thing that changes is G sub S. If it's simply advection dispersion equation, nothing else is happening, you only have S times 1. This is the only term that survives. Everything else goes down to 0. So what this allows us to do, therefore, is to work with many different models, advection, dispersion, or more complex models, but our framework remains the same. And fortunately for us, once we do this, as I said, what we are trying to do is we want to use moment generating function property of Laplace transforms, which means we want to be able to take derivatives of this with respect to S. The first part of it is always the same. The only thing that changes is our derivative with respect to G. Okay, but like I said, taking derivative of this once or twice is far easier than trying to do anything else. Any questions so far?
Are you trying to incorporate sorption into the model, in the PNA model?
Yes.
Physical.
Physical non-equilibrium and chemical non-equilibrium both have sorption in it. Both have absorption in it.
Then what is the difference between these two?
I think it's just a conceptualization. Physical non-equilibrium model assumes that we have two kinds of liquid phases, the mobile water and immobile water. But the solid phase is only one type.
No, okay. In the physical equilibrium model, you have dynamic fluid region
Yes.
and step.
Oops, sorry. So in the physical non-equilibrium model, I have mobile region and immobile region. And then I have one soil region. The soil region essentially is basically part of it is attached to the mobile water, part of it is attached to the immobile water. If it is attached to the mobile water, then this concentration difference, is what it relates it to. So S sub m is related to CMR, SIM is related to CIMR. So in the physical non-equilibrium model, we have two physical water compartments. The soil compartment is essentially the same. It doesn't have different properties, just as whether the soil is attached closer to the mobile water or is it interacting with the immobile water. That's physical non-equilibrium. In chemical non-equilibrium, there is only one water compartment. But the solid soil phase is divided into two compartments now. One where the reaction is instantaneous, one where the exchange takes time. So otherwise they're the same. It's a matter of how we conceptualize it. Physical non-equilibrium, two water compartments, same solid phase compartment. Chemical non-equilibrium, water phase is just one. But soil absorption sites, we have type 1 and type 2 sites. That's a difference. It's a conceptualization difference. I mean, since you bring it up, we'll later on see, when we talk more about temporal moments, I think Professor Srivastava was also talking about non-dimensionalization. We'll do non-dimensionalization. The non-dimensional form of the physical non-equilibrium and chemical non-equilibrium are identical. Which also means, what it means is if you observe the concentration as a function of time or the flux concentration, carry out an experiment, you look at the results. With the results, you cannot distinguish whether within the soil we have physical non-equilibrium occurring or chemical non-equilibrium occurring. Because you have to believe what is happening inside the soil. The signature that you get from the flux concentration cannot tell you that. Yes?
In PNE model, how can you assign weightage to theta m and theta I?
How can you assign weightage?
Mobile water
Am I assigning weightage to them? So I'm saying the total water content is mobile water plus immobile water. So what happens is so there are ways where you can do experiments, and I mean for those of you who do experiments with soil will know this. To find the total saturated water content in the soil column is not actually an easy job. You have to fill water under back pressure and make sure all the pores are occupying the water. And because you have to be able to push water into these pores which are very difficult to reach. To reach them, the water has to pass through some very, very narrow openings, okay? Not easily reachable. And they don't come out very easily also. Okay? So, to basically, then you will find the total saturation or the total water content. You can do other experiments to see which part of it is actually actively playing part in water movement. So that is, the other part doesn't actually actively have water movement. Water exists, but it's locked in dead-end pores and other places. That's the immobile water. So the total water content is going to be theta mobile plus theta immobile. If you wanted to say how would we independently go and measure those two, you would have to do some other experiments to get at them, but that can be done. We don't assign any weightage. A given soil, theta, how much of it is theta mobile or how much of it is theta immobile will depend on the soil. Usually we have soils which are called as aggregated soils. Okay, these are not fines, these are not sands and so on. Soil is in clumps and so on. So within the clumps, there is a lot of pore space. Water can move very easily. The clump itself is like solid clay almost. It has lots of porosity, but the pores are so fine that water enters, cannot come out. So it doesn't actively take or they don't actually take part in water movement. There was another question.
So how do we know which one will get in a particular stream?
We won't. I mean, that's what I'm trying to say, because what we are doing is we are conceptualizing this is what is happening in the soil. Unless somebody can go within the soil and figure out whether it's physical non-equilibrium occurring or chemical non-equilibrium occurring, we do not know. The signal that we get, we observe, is the flux concentration as a function of time at the outer of the soil column. Or we are measuring bulk concentrations throughout the soil column. Neither of these allow us to resolve which of these models is correct or which is the one to use. In fact, later on we will find that we do not actually have to believe the advection dispersion equation types of models also. There's a whole different class of models which we will talk about. So the correct answer is we don't. So we conceptualize that this is what is happening in the soil. Alright, so we'll talk about more of this thing, but what we are trying to illustrate through this lecture is there are many of these kinds of solute transport, advection, dispersion types of models, some more complicated than others, but our strategy has the same form. They all follow the same equation. And as we basically say, eventually all the differences boil down in how this G sub S function is. Otherwise, everything flows through the same way. For the advection dispersion model, G sub S simply happens to be equal to S. For all other models, if you make them more complex, this is where all the action is going to be. And if we are doing moments, like I said, then we are essentially set. So this is a big advantage, I mean, for people who study moments. And this is the idea that Eris had, which says that if you can give me the Laplace transform of the concentration, I can find all moments very easily, because Laplace transform is a moment generating function. That basically helped us do a lot of this. Any questions? My watch is, okay, it's noon. Is it noon now?
It is.
It's noon. All right, so we'll stop over here, and I'm here for a few more minutes if you have any questions. But tomorrow morning, we will essentially start talking about a different class of models. Advection dispersion equation types of model, which you saw, is one class of model, but like you have to believe that advection dispersion is occurring in the soil. Soil doesn't have to believe that. So we'll look at other class of models too, which are perhaps more fundamental, and we'll find out that advection dispersion equation is one of those types of models. But it will allow us to explore different things, and then we will also find out what moments mean in these contexts and so on. So we'll stop over here.